Hello students, today in your geometry class we're going to be discussing medians, altitudes, and circumscribed and inscribed circles. So, to start, there's a lot of definitions, so you want to make sure you're really paying attention to this. So I'm going to read it to you, and then we're going to give you a picture to help you see it a little bit more clearly. Now, Theorem 5.6 states that the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So, we're going to use this picture right here. Now we're going to look at the circle, and it gives us this circle right here on the right hand side. What it does is it says that if we have the perpendicular bisectors of the sides of a triangle, so we have triangle QRS, what it's saying here is that if I were to create perpendicular bisectors, so essentially lines that cut a side in half and are perpendicular, as is the case, let me highlight this for us really quick. Here, this line segment right here is a perpendicular bisector to line segment QR. What it means is that one, it cuts it in half, and it also makes it perpendicular to that side. Now, if we were to do that for all three sides, so for QSR, create a perpendicular bisector, what would end up happening is that those three perpendicular bisectors intersect at a point. And this point, just to make sure it's extra clear, will be colored red. So this point right here in red is our point of concurrency. That's the point where all three lines intersect. So that's what it means for the perpendicular bisectors. Now, what that means, because those three lines, perpendicular bisectors, are concurrent, it means that these three lines in red, or in blue rather, this line in blue, we'll call it CS, line segment CR, and line segment CQ. All three of these points are congruent. It means that they're all the same length. Okay. Rather than going over Theorem 5.7, we're going to talk about what it means for those points to be the same. Now, those 3 points are the point of concurrency, the one in red. This counts as the circumcenter of the triangle. Now, circum usually means to navigate around, but in this case, it's the same thing. The circumcenter of the triangle basically means we're going to create a circle with center C that goes around the triangle, that navigates around the triangle. And because triangle Q, S, and R are all equidistant from point C, then that means that they're all going to serve as the radius, which is why we can draw a circle like they did for us already. Okay, and that will be your circumscribed circumscribed circle, and that's based off of perpendicular bisectors. Now, Theorem 5.7 is similar, but not the same. It says that the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. So, let's use the picture below the one we were just working with to make this a little bit more clear. Now, again, it says the bisectors of the angles. So the bisectors of the angles, it means the lines that cut the angles in half. So if we look at triangle UTV, create an angle bisector for T, that's here, bisector for U, and again, another line segment that cuts it in half, and a line segment, or angle bisector for angle V. They intersect at this point in red, which are also called our point of concurrency. And again, this is for angle bisectors. Now what happens is, this point in the middle creates what's called our in-center of a triangle. And what happens with the in-center of a triangle is that from there we can create an inscribed circle within the triangle. So let's see if we can simplify that a little bit more. It means perpendicular bisectors. Perpendicular bisectors equals circumcenter of a triangle. Angle bisectors translates into inscribed circle in a triangle. So we're going to definitely have to revisit this when we work on our problems, but that should simplify it for now. Next thing we're going to work on is the median of a triangle. Now, the median of a triangle is a lot simpler than the last set of proofs and theorems. The median of a triangle simply states that if you took a triangle and extended a line from the vertex to the opposite side and cut it in half, or essentially bisect it, you created a median. So notice in this instance, I'm creating a line that starts at a point, or a vertex, and I'm extending it to the other side of the triangle, and I'm cutting it in half. When you do that, that's called a median. Now, if you do that for all three sides of a triangle, what happens is you create a point of concurrency right there, and this point of concurrency is also called the centroid. So let's do an arrow really quick. This point right there is called the centroid. Now, Theorem 5.8 states that the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So essentially what this is stating is that line segment DC is 2/3 of the measure of DJ. So what we're looking at here is the line segment for the median, okay? And we're looking at the line segment from the vertex to that point of concurrency, or to the centroid. We're saying the length from a side to the centroid is equal to 2/3 of the whole side. Conversely, that would mean that CJ should be that other 1/3, but we won't deal with that too often. Now the next definition is altitude. The altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. Unlike any angle bisectors and medians, an altitude of a triangle can be a side of a triangle, or it may lie outside the triangle. So if we look at these three definitions, here in the first one we have an acute triangle. In this acute triangle, the altitude starts from a side, or starts from a vertex, and connects straight down to form a perpendicular side. In this case, the altitude is inside the triangle. In a right triangle, the altitude is a side, and in an obtuse triangle, the altitude is on the outside of the triangle. Last but not least, the lines containing the altitudes of a triangle are concurrent at the orthocenter of the triangle. So we are going to talk about this a little bit more in Chapter 6, so I wouldn't worry about it just yet, because we're not going to deal with it too much. What we're going to do now is we're going to practice a little bit. Here, in example 1, it says find the center of a circle that you can circumscribe about each triangle. So if you're paying attention to the notes we did earlier, it says that circumscribed triangles, and we'll pull up our little notes, circumscribed triangles come from the perpendicular bisectors. So let's copy these down, and we'll try. And keep in mind, we use these notes to help us out, especially because this is so new and we've given you tons of definitions. Now, because it says circumscribe, we need to use perpendicular bisectors. So, we're going to start at the middle, we're going to create a bisector. So, for this triangle, we're going to start at the base, the one along the x-axis. This is 1, 2, 3, 4, 5, 6, 7, 8 long. So, I'm going to draw a line going straight up the middle. Same thing for the other two sides. This one is 1, 2, 3, 4 down, and 1, 2, 3, 4 to the right. Therefore, this should be the perpendicular bisector. Notice it cuts it in half and is perpendicular. And same for this guy. Now, we're going to look at where these three lines intersect, and in this instance, they intersect at the point 0, 0. Therefore, the center for our circumscribed triangle is 0, 0. Next one, it says find the center of the circle that you can circumscribe about each triangle. So here they give us the points. So we're going to start off by plotting those points. The first one is 0, 0. Next one is at 4, 0. So 1, 2, 3, 4, 0. Next one is at 4, negative 3. So 4, negative 3. So now we're going to create a quick triangle. Now we're going to do is we're going to create the perpendicular bisectors. So, we grab our line tool. I'm going to change. No, we're going to leave the color. Now, for this, we're going to start at each point and we're going to create a perpendicular bisector to the opposite segment. So in this case, it's sorry, not starting at a point, starting at a side. So right here, we're going to draw a point. It's going to be halfway here, it's going to be perpendicular. We're going to start at this point. So the distance is 1, 2, 3, 4. So we're going to start at 2, and draw another point, and start at this right side. Start at about negative 1.5, and draw a point this way. So keep in mind, for these circumscribes, we don't start at the point, we start at the mid-segment of a side. So here's their point of concurrency, right at the bottom, and that point just happens to be 2, negative 1.5. Now, we're going to try one more. In this case, we have a set of medians. It says, a triangle TV, y is the centroid. Now remember, y being the centroid means that this is the intersection of the three medians. And it says if yu is 9, means yu is 9, they want zy and zu. Now if you remember the rules, it says zu is equal to 2/3, uy is equal to 2/3 of uz. If you notice though, they used yu, so we'll use yu also. Now because that's the case, yu is 9, that's equal to 2/3 of uz. Or to there is they're saying ZU. Now if that's the case, we're going to flip and multiply. So we're going to multiply 3 halves to 9, and 3 halves to 2/3. So this would give us 27 halves equals ZU. So now we found ZU. ZY is what's left over. So therefore, ZY should be equal to ZU minus YU. And the reason why that works is if you look at the picture, ZY is whatever is left over from UZ minus YU. So ZY equals 27 halves minus 9. Makes it easier, we're going to convert that 9 to have a improper fraction, call it 18 halves. Therefore, ZY is equal to 9 halves. And we're done. Now it's your turn to try. I want you to try problem 1 and problem 2. Notice that we've done problems just like this already, so if you need to, please refer back to them in the video. First person, remember to post these onto Edmodo, first person will start, everyone else will reply. That's all for now. See you guys next time.